Well friends, last time we discussed the response of a plasma to radio frequency electric field in the absence of any other field like a magnetic field or anything else. Today I would like to extend that study to electric field that has space dependence and also study the response of a plasma to an electric field in the presence of a DC magnetic field, because most plasmas, if you have to confine them from expansion, stop them from expansion, you employ a static magnetic field, and hence a realistic plasma response would have to be investigated in the presence of a DC magnetic field. But before I go over to discuss the response of a plasma in the presence of a DC magnetic field, let me consider the problem of plasma response to a RF field which depends on a space, and then I will go over to discuss the electron motion in a magnetic field alone, and then plasma response to uniform radio frequency electric field. I will deduce an expression for conductivity tensor, and then I will discuss a important effect called cowling effect. So, in order to understand the response of a plasma to an electric field which varies, whose amplitude varies in position, say r in general, and time dependence was of this form. This is a very important issue. Please understand that the electric field gives rise to velocity to particles. Velocity means their position changes. So, when position changes, r will change with time. So, you cannot take this to be constant. So, there is a inherent or hidden dependence of a on time. Explicitly, a does not depend on time, but because the position of a particle that sees this electric field varies from time to time due to the velocity it acquires due to the RF field, this a has a hidden time dependence. So, this is a serious problem, and I will have to employ the technique of iteration to solve the equation of motion. Let me write down the equation of motion. For the sake of simplicity, I will ignore collisions, I will ignore pressure term, anything. Just consider a simple response of a plasma to an electric field of this form. The equation of motion is m delta v by delta t plus v dot del v is equal to minus E. However, there is a problem here. If there is a time varying electric field with amplitude a function of position, if you take curl of E, it may be 0, it may not be 0. If it is not 0, then third Maxwell equation will tell that there is a magnetic field also associated with there, and hence I must add a term here minus E v cross B. So, this B is the magnetic field associated with a time dependent electric field whose amplitude depends on R. Now, this is a little complicated equation. This is the electric force, this is the magnetic force, which involves the response V also. My goal is to find V due to E. What is the particle velocity due to the electric field E? Well, first let me calculate what is B. From third Maxwell equation, curl of E is equal to minus delta B by delta T in MKS units. And because electric field is changing in time like this, in the steady state B will also change with time like this. So, I can replace this by I omega delta delta T by minus I omega, one I is already, minus is there. So, simply this becomes like this. So, you see here that V is equal to 1 upon I omega curl of E. If my electric field is small, B is also small, and the response V will also be small. So, how do we solve this equation? The terms that depend on the product of small quantities are called small terms. Like V, if I multiply with another V here, this is really product of very small quantities, it will be much smaller than this term. Similarly, V is a small response, a small velocity if my E is not large, and B also will be small because E is not large. So, this is a product of two small quantities and you can ignore them. So, we solve this equation iteratively by first ignoring this term and this term. Rather than ignoring them, let me rewrite this equation like this: m delta V by delta T is equal to minus EE. So, take this term on the right hand side, it becomes minus m V dot del V minus E V cross B. These two terms are called nonlinear terms because they are the product of small quantities and they have the dimensions of force. So, I can combine them together from here to here and give a name to them. In literature, the name given to them is Fp, nonlinear force, also called Ponderomotive force. So, I would like to calculate the value of this iteratively. First of all, I will ignore the Ponderomotive force, obtain the response of electrons to the electric field alone, and then use the value that I will calculate here in these terms and evaluate those terms. Let us do that. So, through the zeroth order, what do I get? M delta V by delta T is equal to minus EE, and because this has simple time dependence of the form exponential minus I omega t. So, velocity also I would expect to have time dependence of the form exponential minus I omega t. Hence, delta delta t I will replace by minus I omega as I discussed earlier. Put this in here, you will get the velocity of the electron is equal to EE upon m I omega. So, now my goal is to calculate the Ponderomotive force Fp, which is equal to minus m V dot del V minus E V cross B. I will have to use the complex number identity to evaluate these products, because here really real part of V is to be placed here and real part of V has to be used here. Similarly, real part of B has to be used there. So, it is a product of real part of V into real part of this quantity. Similarly, real part of V is to be multiplied with the real part of capital B there. What should I do? I can write this as minus m real part of, so real part is implied, I will not write explicitly the symbol Re, but it is implied, or let me write this half there, and V dot del V. I am not interested in time dependent part of Ponderomotive force for the moment, I want time independent part of Ponderomotive force. So, I will take only complex conjugate term. I just explained in my previous lecture that when you have to multiply terms, then there are always two terms, one without complex conjugate, the other one with complex conjugate. The term with complex conjugate, the exponentials cancel out. So, this becomes a time independent term. So, I will write only that, and then here it becomes E by 2 real part of V cross B star. So, this is time average point motive force. Otherwise, I should write two more terms. I will not write them. Let me evaluate this number, this expression, this force. What do you get here? V, if I substitute from here and takes complex conjugate there, this becomes simply equal to E square, one E is there, one E is there, so E square, M square comes in the denominator, one M will cancel out with this. So, E square upon 2m omega square will be common, and it will be real part of E dot del E star minus, if I put the value of V again here, it becomes E square upon 2m. Now, I omega is there, but B also has. So, let me just remind you, well, I think let me put this, do it in two steps. I omega is because of this. I think I should cancel this here because the real part I have to take. So, this becomes E square upon 2m omega outside, and this becomes 1 upon I into E cross B star. So, I just substituted the value of V from this expression in here and taken the constant terms outside, imaginary term I should keep inside. This is what you get. Let me remind you that B I had written as 1 upon I omega curl of E. So, use there. So, B star will be minus 1 upon I omega into curl of E star, complex conjugate of E. So, if I use this in the expression for Fp, Fp becomes equal to, I think I forgot the first term was a negative sign also. In the previous case, it was actually had a negative term, minus E square upon twice m omega square, and real part of E dot del E star minus E square upon twice m omega square, and you will get real part of E cross curl of E star. This factor is common in both the terms, and you always know that real part of any complex number C is the same thing as half C plus C star. If there is any complex number, if you add its complex conjugate with it, the imaginary parts will cancel out, and this is always true. This is always this. So, now this is a complex number in general. What I can do? I can write this expression as this expression plus its complex conjugate divided by 2. So, Fp becomes minus E square upon 4m omega square, and this becomes E dot del E star plus complex conjugate of this quantity, which is E star dot grad E. Just reverse the stars. Similarly, here this is plus E cross curl of E star plus E star cross curl of E. This is a very general expression for ponderomotive force due to a RF field which does not depend, whose amplitude does not depend on time but depends on space, and this could be arbitrary space dependence. So, this is general expression. Now, please put this E in terms of A, then this can be written simply as minus E square upon 4m omega square. All the exponential factors will cancel out because they are complex conjugate terms, and they will be simply A dot del A star plus A star dot del A plus A cross A star here plus A star cross curl of A. This is a vector quantity. It has x component, y component and z component. I will evaluate only one component fpx, and then I will generalize to, similarly I will write down y and z components. Let me write down the x component for a general case. Fpx will be how much? Let us see. Fpx would be minus E square upon 4 m omega square out. Now, the first term was A dot del A star. So, I am writing x component, so this will be A dot del of A star x component. I should write here, forget this sign here, because A dot del is a scalar quantity. So, when I had written A star, I should write like this, plus second term was A star dot del, which is a scalar quantity. So, total quantity has to be written, and A was there, so put Ax there. Similarly, A cross curl of A star, I want x component. Let me write this simply, A cross curl of A star, I want its x component, and then I want x component is quantity A star cross curl of A, x component of this quantity I want. Let me simplify this. This is equal to minus E square upon 4m omega square. A dot del has 3 terms. This is Ax delta delta x of Ax star plus Ay delta delta y of Ax star plus Az delta delta z of Ax star. Please remember, A dot del is a scalar product, so it has Ax delta delta x plus Ay delta delta y plus Az delta delta z, and all the 3 components have to be added, but this they all operate over Ax star. Similarly, second term will give me plus Ax star delta delta x of Ax plus ay star delta delta y of ax plus az star delta delta z of ax. Then the x component of this product, which is a little complicated, but it is not that bad. So, like treat this as one vector, this as another vector, a cross b kind of thing. So, I will get x component of this quantity means y here, z there, minus z here, y there. So, this will be x component will be ay multiplied by z component of this quantity. Z component means x y minus yx. So, delta delta x of a y star minus delta delta y of ax star. This is ay into z component of this quantity minus z component of this and y component of this. So, y component of this quantity would be delta delta z of ax star minus delta delta x of az star. I am very explicit on this because this is something which is very useful, very important in nonlinear plasma theory. So, the derivation of this I am really doing step by step, so that you have some feeling for this. Plus I have to write down the x component of this quantity, which is very similar to this one, only the stars are interchanged. So, this becomes ay star delta delta x of ay minus delta delta y of ax minus az star delta delta z of ax minus delta delta x of az, like this. I am sorry, I have been very explicit, but this is useful. Now, you may note here that only two terms survive, others cancel out, not two means most of the terms cancel out. For instance, this term ay delta delta y, you will find ay delta delta y here as well, ay delta delta y of ax star, this term will cancel with this term. This az delta delta z ax star term, az delta delta z of ax star term, this will cancel out with this. Then this term, this will survive, ay star delta delta y, ay star delta delta y, ax, this is negative, this is positive, they will cancel. Then this az star delta delta z, az star delta delta z of ax, this will cancel out with this one. So, lot of terms have cancelled out. What you are left with, this is ax delta delta x of ax star, and this is, these two terms can be combined, become delta delta x of ax star, ax star. Similarly, this term delta delta x is common, so it becomes, this term can be combined with ay term, this one. So, these two can be combined. So, this can be combined with this term, this can be combined with this term, and this term can be combined with the last one. They are of same sign. So, this can be combined with this term, and when you combine them, you get a simple expression minus e square by 4 m omega square delta delta x of ax star plus ay star plus az star. Let me rewrite this expression. This becomes, so the x component of quantum motive force is simple, minus e square upon 4 m omega A square delta delta x of modulus of A square. So, this is not vector, this is a scalar quantity x component. Similarly, if you had calculated the y component, z component, then you will write f p vector is equal to minus E square upon 4 m omega A square del operator operating over A square modulus of A square. But modulus of A is the same as modulus of the electric field. So, minus E square upon 4 m omega A square gradient of E square. This quantity is very important in plasma theory, plasma physics. What does it tell? This says that if in a region of a space electric field has a non-uniform amplitude, suppose the electric field has a larger value here and a smaller value there, then the gradient of electric field is in this direction, the force will be opposite, means this force compels the electron to go from high field region, this is the high field region for instance, to low field region. So, electrons will go like this, they will flow out. It is a very important consequence. It has a very important consequence in plasmas, because if you are sending for instance a high power laser in a plasma, the intensity of the laser is large on the axis and small outside. So, when the laser goes into a plasma, the electric field is large on the laser axis and less outside. So, laser repels the electrons from the central region or axial region to outside, creating a plasma channel. This nonlinear force has been recognized, has been measured and has been observed in numerous experiments and has been found to play a very important role in laser guiding and many other nonlinear phenomena. Here I have calculated only the time average part of this quantum motive force. If you had calculated the time dependent part of quantum motive force, this is responsible for harmonic generation, which is another important nonlinear effect. So, I think in our response of plasma to radio frequency field, we have learnt that the radio frequency response at low fields can be described in terms of a quantity called plasma conductivity, but when the fields are strong and when they become time or space dependent, in that case an additional response term or force acts on the particles, which is called quantum motive force. What is the response of plasma to this force, we shall discuss later on when we discuss the phenomenon of self-focusing, maybe a few lectures later. So, I think with this we conclude our discussion on radio conductivity or radio frequency response of a plasma in the absence of a magnetic field. Now, I would like to take you to the plasma response in the presence of a static magnetic field. A static magnetic field in the easiest form can be written as B static, which is independent of position and time, and let us suppose the direction I choose to be in the z direction. First of all, I would like to see what an individual electron will do in the presence of a magnetic field, and then later on I will discuss, if you have millions and trillions of electrons, so electron as a family, electron as a community, how do they respond to this magnetic field, or in the presence of magnetic field, how do they respond to the electric field. So, first of all, let me do the single particle effect. Well, suppose this is my z axis where I have applied my DC magnetic field. If I launch any electron in the system which is moving with some velocity here, for instance, you know that the velocity of the particle can be resolved into two components, one along the magnetic field and one perpendicular. The electron will experience a force. The force will be charge of the electron into velocity of the electron cross B. This is the force on the electron, and the equation of motion would be m dv by dt. For a single electron, this is the equation of motion. So, what will happen? The electron, physically let us understand what happens. The electron velocity you can resolve into two components, one parallel to magnetic field, one perpendicular. The component of velocity which is parallel to magnetic field, the force vanishes. Only because of the perpendicular velocity, this will experience a force, and this will try to, the force will be perpendicular to both the velocity and magnetic field. So, perpendicular plane of the board, and the electron gyrates about the line of force, and that motion can be easily understood from this equation. If I divide this equation by m and I define a quantity E Bs upon m is equal to omega c, for instance. So, this equation becomes dV by dt is equal to minus V cross omega c. Well, omega c is a vector parallel to z axis, because the static magnetic field is the z direction. So, I want to solve this equation, a simple equation, but this has very rich physics. First of all, I will write down the z component of this equation. It becomes dvz by dt equal to 0, which means that the particle velocity in the z direction will be constant. Secondly, I write down the x component. That would give me dvx by dt is equal to v cross omega c. If you write down the x component, it will be minus v by omega c, and then write down the y component of the equation of motion, dvy by dt is equal to vx omega c. The x and y components of velocity equations are coupled. So, what you should do, take the time derivative of the first equation, you will get d2 vx by dt square is equal to minus omega c is already there, dvy by dt. Now, use the value of dvy by dt from here, it becomes minus omega c square vx, and a general solution of this equation can be written, and let me write down that solution. That solution is Vx is equal to some constant, let me call this constant as A cos omega ct plus another constant. A second order differential equation has two constants. So, this is one constant, this is another constant, and if Vx is like this, and if you use the x component equation of motion, then Vy can be obtained to be equal to A sin omega ct plus delta. So, I have substituted the value of Vx in the x component of equation of motion, and I get the value of Vy. So, these two I obtain, and you may note one thing in here, that Vx square plus Vy square, if I add, they give me A square. So, A is a constant, means Vx square plus Vy square is a constant. This is usually given a symbol V perp square. So, rather than writing A, I will write down a symbol V perp. Then this equation becomes Vx is equal to V perp cos of omega ct plus delta, but Vx is the same thing as dx by dt. So, I can integrate this equation to obtain x as a function of time, because V perp is a constant and this time dependence is simple. So, x turns out to be some constant, let me call this constant as xg, plus V perp upon omega c sine of omega ct plus delta. And similarly, if you solve this equation for Vy, you will get y is equal to yg, a constant yg, minus V perp upon omega c cos omega ct plus delta. This is a very general expression, but the beauty here is that if I take x minus xg square and add y minus yg square to it, you will find this again a constant. So, these two equations give me x minus xg whole square plus y minus yg whole square is equal to V perp square upon omega c square. This quantity is given a symbol called rho or Larmor radius. This is the equation of a circle whose center is at xg yg and whose radius is rho, which is V perp upon omega c. And so, the electron really rotates on a circle. If you draw a graph of, suppose I plot here Vx and Vy here, and Vx I have taken is equal to V perp cos omega ct plus delta, and Vy is equal to V perp sine of omega ct plus delta. Now, if you plot, for the sake of specificness, suppose I choose delta equal to 0, it really does not matter what delta you choose. At delta equal to 0, at time t equal to 0, Vx will be V perp and Vy will be 0. So, you are somewhere here. At a later time, this quantity will decrease, this will increase, and this electron will rotate like this. So, this is the way the electron will move. The electron was initially here, it went from here to here, then here and everywhere. So, this is rotating in a sense that if I take a right handed screw and rotate along the path of this like this, if I rotate it like this, then this will advance in the direction of z axis. This electron motion is known as right circularly polarized motion, right circularly polarized, or it is rotating in the right handed sense. Similarly, if I plot x here, particle coordinate x there and particle coordinate y there, then around a point xg yg, the electron will rotate over a circle, and the coordinates are like this. This coordinate are xg yg, and this radius is r, rho rather, and the electron is rotating like this. So, what is happening, that the electrons rotate about a line of force. They can move along the line of force with velocity Vz, but they cannot leave the line of force. So, whenever there is a magnetic field in the plasma, the electrons, in the absence of any other force, I am considering no collisions, no temperature variation, nothing except a DC magnetic field which is uniform. So, if you have lines of force like this, then the electrons move along the line of force like this, but they do not move perpendicular to the line of force. So, in a way, the electrons are confined to the lines of force, and magnetic field provides a confinement to the plasma. Obviously, there is a problem that what would you do? Either you find some sort of a reflection of electrons along the lines of force by some mechanism, or do something or close the line of force, only then you can confine the plasma, but that is a separate issue. So, but we have really found something very significant, that a single electron in the absence of any other force will not move perpendicular to the line of force. Now, I would like to examine the effect of a DC magnetic field, DC electric field, RF electric field on the electrons in the presence of a magnetic field. So, my issue is, I have a plasma in which I am applying a electric field of this form, whose amplitude is constant in time. The field is independent of position coordinate also, and I would like to examine the response of the plasma when there is a static magnetic field also, which is equal to Bs in the z direction. So, the electric field of the RF can have a component along z axis, and it can also have components perpendicular to B. Let us see what is the response. Because we are ignoring any space dependence, so the equation of motion then in this case would be m delta V by delta t plus V dot del V is equal to minus E minus E V cross Bs, which is in the z direction. This is my equation of motion. I take this term to be 0 because V does not depend on x, y, z. So, then if I divide this equation by m, my equation becomes delta V by delta t I will take this term on the left hand side. So, it becomes plus V cross omega c is equal to minus E upon m. Please remember, omega c I am defining as E Bs upon m. The same omega c was appearing in the equation of motion in a pure electric magnetic field, and this is known as the electron cyclotron frequency, because the electron rotates with this frequency around the line of force. So, I have to solve this equation, because my time dependence of the electric field is like this. In the steady state, I expect the V also to have same time dependence. Hence, I will replace delta t operator by minus I omega, and let us see what do I get. So, by replacing delta t by minus I omega, my equation of motion becomes minus I omega V plus V cross omega c is equal to minus E upon m. If there were collisions, then I should use a collision term also, which will be minus nu V. This is the collision term I can add, and this can be combined easily with this V term here. So, it becomes, this is the collision term. In many cases you can ignore this, but for the sake of completeness one can include this here. So, you get nu minus I omega into V plus V cross omega c is equal to minus E upon m. I will write down different components of this equation. Let me begin with the simplest one, which is z component, because this term vanishes. So, V z turns out to be E upon m nu minus I omega with a negative sign. Then write down this x component of this equation, I can write down this x component is equal to minus I, actually take minus I out, omega plus I nu inside into Vx, this will become Vy omega c is equal to minus Ex upon m. This is my x component of this equation. Similarly, I will write down the y component, which turns out to be equal to minus I omega plus I nu into Vy minus Vx into omega c is equal to minus Ey upon m. These equations are coupled algebraic equations for Vx and Vy, which can be solved to obtain Vx and Vy, and I will simply write the value of Vx and Vy separately. This turns out to be is equal to E upon m omega plus I nu whole square minus omega c square multiplied by minus I omega plus I nu into Ex minus omega c Ey, this sort of expression you get, and Vy can simply be written Vx is equal to this expression I have correctly written, and Vy is the same similar expression E upon m omega plus I nu whole square minus omega c square into minus I omega plus I nu into Ey plus omega c Ex. Once we know the velocities of the particles, or drift velocities of the electrons, you can write down the current density. Current density due to electrons I will write as minus NeV. You may note one thing, Vx involves not only Ex, it involves Ey also. Vy involves not only Ey, it involves Ex also. Means one component of J will involve not only the electric field, that component, but other components of electric field also. So Jx will involve Jy besides Ex, Jy will involve Ex besides Ey, and so on. So in general, if I substitute this V in this one, I can write down sigma E, electron conductivity, dot E. It's a symbolic representation. Sigma is a tensor called conductivity tensor, and this implies that if I have to write down Je, electron current density, x component, then I must write down the x component here. Now this tensor has two indices, sigma E, so I should write down the first index is the same as of x of J, and other is running. So like this is Jxx Ex plus sigma E xy Ey plus sigma E xz Ez. This is the meaning of the by definition. So in tensor representation, Jx is a scalar quantity, so I should not put a vector sign there. Like this, similarly you can write down Jey. So if you compare the coefficients of Ex in x component of current density, you will write down the value of sigma Exx, sigma Exy, sigma Exz, and if you evaluate these quantities, you get this expression. The expression is sigma is a tensor electron conductivity, which is equal to the following components are finite: sigma Exx, this is sigma Exy, sigma E x z is 0, sigma E yx component is equal to sigma E x y with a negative sign, sigma E y y is equal to sigma E x x, this is 0, this is 0, this is 0, and this is sigma E z z, where these values are sigma E x x turns out to be equal to n E square upon m, and here is omega plus I nu whole square minus omega c square multiplied by I omega plus I nu. This is I think this is correct expression, and sigma E x y is equal to n E square upon m omega plus I nu whole square minus omega c square into omega c, and sigma E z z is equal to n E square upon m nu minus I omega. So, this is a tensor, and the tensor has non-diagonal terms finite, and they are of opposite sign. The diagonal terms are, two of them are equal, but the third one is not equal. So, this is a characteristic, this anisotropy is a characteristic of a magnetic field or a magnetized plasma. You may note one thing more here. If you forget collisions, because collisions are usually a very small quantity, if you forget collisions, then this can be written as n E square I omega upon m omega square minus omega c square. There is a cyclotron resonance effect here. When the frequency of the electric field is close to the cyclotron frequency of electrons, in that case this quantity could be very huge. And similarly, this quantity n E square omega c upon m omega square minus omega c square could also be huge. So, this is one important consequence of applying a magnetic field. So, magnetic field not only confines the plasma, it can enhance the conductivity immensely in the vicinity of cyclotron frequency. Secondly, if omega is less than omega c, much less than omega c, then sigma E x x goes as m into omega c square. In the case of ions, if you write ion conductivity, these expressions are valid. Just replace mass of the electron by mass of the ion and omega c by ion cyclotron frequency, which is very small quantity. And it is possible that ion cyclotron frequency, ion conductivity could be comparable or even bigger than the electron conductivity. That is a very important consequence of magnetic field, and this presence of the cyclotron resonance effect at electron cyclotron frequency as well as at ion cyclotron frequency gives rise to very important wave phenomena that are useful in exploring space plasmas as well as laboratory plasmas. It has tremendous consequence on wave propagation, Alphen waves, Whistler waves, upper hybrid waves, lower hybrid waves, and so on. There are all sorts of waves in a magnetized plasma that are possible because of the cyclotron effects, electron Bernstein wave, ion Bernstein wave, and so on. So, I think plasma response is very strongly influenced by the presence of magnetic field, and ion dynamics cannot be ignored in general. Obviously, at high frequencies, when omega is comparable to omega c, much bigger than the ion cyclotron frequency, you can ignore the ion motion, but at lower frequencies you cannot. So, I think we have to study a little more carefully the consequence of magnetic field in plasmas. I think this is one thing, the derivation of conductivity tensor. I think it will be very useful if you can go step by step and appreciate this, because when we study the structures which have non-uniform magnetic field, then the particle dynamics becomes a little more complicated, but the understanding of this tensor will help us in understanding more complex geometries. So, I think I will close here today. Today we have really developed a general formalism of, rather general framework to study the wave phenomena in plasmas that we will undertake later. Thank you.